Okay, hello everyone. Welcome to this extremely short video, power system analysis. The idea of this video is discuss some aspect about the use of PowerFactory in order to calculate the short circuit currents. Okay. This is just a very brief and very short explanation about short circuit calculations using the DIgSILENT PowerFactory. Okay. Okay, please remember for this example you need to download one example that is included in my GitHub, and also the slides can be found at my ResearchGate. Okay, of course, if you are watching this, it's because you are subscribed to my YouTube channel. If you have time, and also if you're interested, could you follow me at Twitter or LinkedIn? Okay. Before we start with the serious business here, I must be honest. If you are looking for a deep explanation about the short circuit calculation function inside the DIgSILENT PowerFactory, please don't keep watching this video, because this video is mainly a very short and very basic explanation. It's intended to show how to use the DIgSILENT PowerFactory for academic purposes. I mean, if you are teaching power system analysis and you are interested to show to your students some numerical results and comparing the equations that you are teaching, especially Thevenin Method and for short circuit currents, and if you would like to show that you are properly right, you can use the DIgSILENT PowerFactory for these academic purposes. Okay. If you are looking at a full detailed video about the full functionality of short circuit analysis in PowerFactory, I mean, if you need to understand how to run consultancy with ANSI or with IC, DIN, or any kind of standardized calculations for short circuit, this is not the video for you, I'm afraid. Okay. What is the job today? The job today, sorry, is to present a very brief and limited vision about the short circuit calculation function inside the DIgSILENT PowerFactory. Okay, to be honest, this example is extremely simple. Some of my colleagues will say that this is extremely basic. You are wasting your time, but here what I want to do is just a short introduction about three-phase short circuits. In this example, I will use unloaded radial distribution system. Okay, and to present the results, I will use the Thevenin method, and I will compare with the results on the DIgSILENT PowerFactory using the complete method. Okay, let's start here. Okay. If you are following me my classes about power system protection, you will realize that I use this example for explaining what is the difference of using discrimination by time or using discrimination by current. And to explain discrimination by current, I use this example and I calculate the short circuits, the three-phase short circuit currents. Okay. The first case here is I would like to show you the short circuit calculation at the point F1. Okay. Well, before we start, let me show you some manual calculations, and probably from there we can start to discuss something. Okay. If you look over here, you can see that we have on the top the single line diagram. Yes. And if you are interested to create the equivalent, the reactance equivalent circuit, you must remember this is the bus bar C, and because you are using here an equivalent source, you can create or use as model an ideal voltage source. Let's say this is, and here you can use an external reactance. Yes. Then you have a cable. You go to bus bar B. Then you have another cable going to the transformer. Finally, there is external point here and going downstairs, okay? This is A, this is B, this is C, okay? We have reactance here for the cable 1. We have reactance here for the line 2, let's call the line 2. Here we have the reactant for the transformer, okay? Let's call these the lines, okay? Okay, simple to fix. This is the line 1, okay? Okay, if we are interested on the short circuit at F1, is the same to calculating the short circuit here, yes? This is the three-phase fault, and this is F1, okay? If you are interested in using the Thevenin method, the Thevenin method, what is looking is into creating a simplified circuit that you have here, the Thevenin reactance, yes? You have a Thevenin voltage, yes? And this is the terminal that we are applying the fault. This is F1. And here we have the fault current, okay? Yes? The Thevenin method, all the problem is calculating the Thevenin voltage and calculating the Thevenin reactance in this case, okay? I believe all of you are aware that there are no load currents in this system. And because they are not load currents, all the voltages are equal on those bus bars. Circuit theory say that. And because they are not loads, and we are assuming that all of them has the same voltage, and we will say that that voltage is the nominal voltage. As a consequence, Thevenin voltage is equal 1 per unit, okay? Assuming that we are using as a base if we are using as a base the nominal voltage, okay? However, if you are using real units, you must remember the following. This is a line to neutral model, and if you are using real units, voltage 1 per unit should be equal to the nominal voltage, that is 11 volts, 11,000 volts divided by square root 3, 0 degree, and this is the voltage, okay? You must remember that this is the line to neutral voltage because we are using the line to neutral equivalent model, okay? Then, what is the next step? Okay, next step is extremely simple. Next step is, how do we create the Thevenin equivalent model? Okay, what we need to do is switch off this voltage source by using a short circuit that represents voltage equals 0 and calculating the Thevenin equivalent impedance, okay? What I'm trying to say is that now we can use this circuit over here. This is the external source. Here the voltage is off. This is the bus bar C. This is the line. And this is the fault point, F1, okay? What we need to do is calculate here Thevenin reactance, okay? In this case, it's extremely simple. It's the sum of the source plus the transmission line, okay? If we are using ohms, you must remember that from here we can see the calculations. Let me show you the calculations. We know that the source is equivalent to 11 kV line to line and a three-phase power of 250 MVA, okay? What we need to know is that the reactance of the external grid, it will be 11 kV, that is the voltage, divided by the power, 250 MVA, and from there it's very simple that you can see also my screen here that value is 0.484 ohms, okay? For the line there is no problem because we know the value, the X, the S from the line is equal to 0.484 0.24 ohms. And now what we need to know is, okay, I want to know the short circuit current, and that is 0.484 plus 0.24. That means that the equivalent Thevenin reactance is equal to 0.724 ohms. Okay? Okay. Now that is the reactance. And here we have 11 kV divided by square root 3. And this is the point F1. And we can calculate the current that is going in this short circuit using real units. 11 kV divided by square root 3 kV divided by the total reactance 0.724J, and as a consequence the fault current will be around 8.8 kilo amps. Okay. Well, what I have done here is just a basic calculation. I show you, you can use Thevenin method using per unit system, or if you wish, you can use real units. I did here real units. What you need to be careful when you are using real units is the three-phase properties, okay? What is important and relevant here is you can obtain the three-phase current at the fault point F1, okay? And this is the short current at maximum generation, okay? Now, let's see if we can do the same using DIgSILENT PowerFactory. Of course we can do, okay? Let's go to DIgSILENT PowerFactory, okay? I already create the system here. I believe all of you can see they are bus bar A, transformer T1, cable 2, cable 1, and then we are going to the external source, okay? I know that some of my top expert colleagues and friends using DIgSILENT PowerFactory, they will say, why you are using a voltage source? Okay, because the voltage source is the most simple way that I can show to my students the short circuit current. I don't want to go into complications at this moment. I am using just 11 kV. You can see here 11 kV line-to-line voltage source. And for the reactance, I am using the value that I already calculate, 0.484, okay? Then we have a cable here, section cable between B and C. I already say to you that this cable has a reactance, and this reactance is 0.24, okay? Then we have another cable, that is the cable between the sections between section B and the transformer, 11 kV, and here is the reactance, 0.04. And finally, we have here the transformer. We have a 4 MVA transformer transforming from 11 kV to, in this case, is 3.3 kilovolts, and the transformer ratio, the impedance is 7%. Okay. Okay. We have the system ready for the calculations, but before I start with the calculations, I would like to do something very basic. You must know that the command for short circuit analysis is located. You can find the command at the toolbar. Okay. If you press the button, we will open the short circuit calculation function. Okay. This is the command. This is the command COM SHC. This is the short circuit command, okay? I would like that you select from here. There are different methods. Some people from consultancy probably they are willing and interested to know about BDE, IEC, ANSI, and so on. But in this class, I'm sorry, I am just dealing for a very basic introduction about short circuits. I will go for the complete method. The complete method is the most simple method and is similar to the classes that we provide to the students about the short circuit analysis. Okay, that is the reason that I will be using this one. Okay, there are few options that we can run the short circuit analysis. One way can be using this command, but also there is another way. Okay. Some of my colleagues that they are a bit faster with DIgSILENT PowerFactory, they prefer this functionality that is the context menu. Okay. What you do is select the transmission line because we want the short circuit at the very end of the transmission line. And we will say, okay, I would like to run, I want to run a calculation, and now I would like to calculate a short circuit, okay? What PowerFactory is doing for me is already defining the settings that I already have, complete short circuit for three-phase calculation, and it's already selecting the device that I want to use for my calculations. In this case, it's the cable. I will say that I want the short circuit current at the very end. That means that 100% of the total length of this cable, okay? Voila! We have results over here. I believe all of you can see that PowerFactory has already presented here a small symbol indicating that the short circuit is at the very end of the cable. And in this case, there are some information presented over here. In this case, it's presenting some results. One of them or two of them, you can see that is 8.772 kiloamps, okay? Okay, what is happening here is that PowerFactory is showing me the short circuit calculation, okay? And I believe all of you can see that the results at the moment is 8.772 kiloamps, okay? We can compare those results with the numerical values that I was showing you at the presentation here, and let's go to the default at F1. I can see here that the as you can see here, my numerical results by hand, I got around 8.8 kiloamps. If you use if you look over here, my numerical results using Thevenin Method, 8.8 kiloamps. If you put the numbers with the proper decimal places, the exact value should be 8,771.896 amps. That is equivalent to 8.8 kiloamps. Okay. Let's see what is nets in this presentation. Okay, nets in this presentation is okay. Let's calculate the short circuit current, but now let's calculate the short circuit current here at the very beginning of the cable number 2. Okay, the fault point is the fault point 2. Okay, let's go again to PowerFactory. Okay, let's go to PowerFactory. And now what we can do is the following. Instead of having the fault here, now the cable that we want the fault is this one. Now right click, okay, calculate the short circuit. Fine. And in this case, we would like to calculate the fault at 0%, yes, 0%, 0 kilometers coming from the bus bar B. And we execute the short circuit calculations. There are no surprises. If we come back to the presentation, we can see that there is not impedance between F1 and F4. It's almost the same place. It's almost the same short circuit current. Okay. What we want to do now, is, okay, what happened if suddenly the generation decrease? I mean, the capacity from 250 MVA is reduced to 230. Well, it's very simple. As you can see over there, there is a simple calculation to obtain the series or the source impedance. In this case, the source impedance is 0.9302. Okay? What I will do now is I will go back to PowerFactory. Now I will modify the reactance, sorry, 9307. Okay, now we modify the source impedance, and now again we want to see how much is the fault current here at the cable. Let's select the cable. We select the cable, then we say calculate short circuit, and now we want that it will be 100% from starting from the terminal I that is represented by the bus bar Z. Okay. Now, what is the result? Using PowerFactory, we will get a 5.425 kiloamps. Let's go back to our presentation. If we go back to our presentation, so all of you can see here the results, numerical results is 5.40 kiloamps. Okay, and what's about the short circuit at bus bar C? Let's see how much is the short circuit at bus bar C. Okay, let's go back to PowerFactory. We are now in PowerFactory. Now we want to run. We want to calculate the short circuit. Okay, very simple. Calculate short circuit at bus bar C. Very simple. Run the calculations, and PowerFactory is showing here. Oh, it's showing two interesting things. Okay, the first thing that you must realize is that the short circuit current is presented over there. Okay, and as you can see over there, let me edit this in order to include all the variables. Okay, and also I would like to show you the units because I want that my students learn something quite interesting here. Let's say yes, adapt width. Yes. Okay, what is showing here PowerFactory? PowerFactory is showing here the short circuit currents, of course, 6.824 kiloamps, but also I configure here the result bots in order to show you the short circuit impedance. Okay, and as you can see here, we are showing the total resistance, the total reactance, and the total impedance. Okay, in this case, you can see that the total reactance is 0.931, and that is quite interesting because if you come back to the PowerPoint presentation, as you can see here, the result is the same, 6823, and the most interesting part is that we are showing that the reactance, that the Thevenin reactance is 0.9307 ohms. Let's go to PowerFactory to show you again, in any case, in any depth. And you can see here is 6.824 kiloamps, and the reactance is 0.931 ohms. Okay. Finally, what we want to see is let's calculate the short circuit currents. Let's calculate the short circuit currents at the very end of the feeder. Okay. Now, considering that we are using the low power scenario, 150 MVA at the source, we want to know what is the, no, let's do the following. Let's do it here. F3, calculate short circuit, calculate short circuit. Let's run the short circuit analysis. Let's show the results. Please show me the result. That's bot says. Show result bot says. And right now what we can see here is that the short circuit current at that width, what we can see here is that the short circuit current at F3 is around 5.246 kiloamps. Let's see the result using Thevenin method. Going back, I believe all of you can see that the result, that the result is here. We can see that the numerical result is for 5.246 kiloamps. And let me run now the simulation when we have the low generation scenario. Okay, let's go back to PowerFactory. Now in PowerFactory, what we want to do is change the source impedance to 484. That is the high generation scenario. Now let's run again the short circuit calculation, and we got as result 8.313 kiloamps. And if we go back to PowerFactory, to the presentation, we can identify here 8.321. Okay, that means PowerFactory and Thevenin equivalent methods, they are providing the same results. Okay, at the moment I would like to say this is all for this short video. The idea was to make a short introduction about the short circuit analysis function and be able to demonstrate to my students that using Thevenin equivalent model, using hand calculation, you can get the same results, and those results can be compared with PowerFactory. Okay, what I want to tell you is a lot of people say, okay, why do I need to know Thevenin method if we have a software that is doing the job? Okay, in real life, in a very big system, you will be using the software, because it's almost impossible having manual calculations and calculating Thevenin impedance and so on. However, if you understand the basics, if you can understand where the Thevenin impedance is coming from, and if you understand the method, you will be able to explain your results. There is nothing something that is quite typical is that if you make a mistake introducing data in a software, the result will be a disaster. And if you are not familiar with the theory, if you are not familiar with the method, probably you will never see the error or mistake, and that could be extremely painful, extremely dangerous. Okay. Well, I would like to close this session saying that DIgSILENT PowerFactory is extremely helpful software, but it's like a calculator, okay? You must know how to put the data inside and how to get the results. But more important than that is when you get the results, you need to be able to interpret and to use those results to create proper real solutions, okay? Thank you very much for coming to this video. Thank you very much. That's all for today. Thanks.